Supernodes are useful, but they can be sort of mysterious. In this video, I'll talk about how supernodes actually work and why they are so useful. During this process, I'll show how to do nodal analysis without using supernodes. The goal here is to help you understand how much effort they can actually save. First, I'll review the basic concepts associated with using supernodes in nodal analysis. Supernodes are useful when the circuit contains voltage sources or equivalently dependent nodes. In nodal analysis, supernodes are placed around dependent nodes to form a single node out of multiple nodes. Essentially, you put voltage sources inside supernodes. Then you apply KCL to the entire supernode, so you sum all of the currents entering or leaving the supernode rather than at each of the individual nodes inside the supernode. The advantage of this is that you eliminate the currents through the voltage sources as unknowns. In order to help understand what's involved in this process, let's talk about nodes, supernodes, and a more general form of Kirchhoff's current law. As we've said before, a node is an area in a circuit that has a single unique voltage. The only circuit elements that can be inside a node are perfect conductors, which introduce no voltage differences. A supernode, on the other hand, is an enclosed surface containing some portion of a circuit. So a node is actually a special type of supernode that contains only perfect conductors. As an example, let's take a look at this section of a larger circuit. If I do KCL at node A, I get this equation. I1 plus I2 plus I4 is equal to 0. KCL at node B gives me this equation. Negative I2, it's entering B, plus I3 plus I5 is equal to 0. If I add these two equations together, I get this equation. The I2 term cancels out of the two equations. Now if I draw a supernode around nodes A and B, I get this same equation. I1 plus I4 plus I5 plus I3 is equal to 0. It includes the cancellation of I2 from these two equations automatically. If I'm not interested in the current I2, using a supernode can result in less effort since we eliminate one unknown and one equation automatically. Since in nodal analysis we're just interested in the node voltages, defining the current through a voltage source doesn't benefit us. Therefore, defining supernodes around voltage sources eliminates an unknown that we have no use for anyway. Having said that, you don't have to use supernodes in nodal analysis if you don't want to. In our example circuit from the previous video, we had 4 nodes. 2 of those were dependent. However, if we don't want to treat these 2 nodes as being dependent, we're free to assign them each variable names as if they were independent. In this case, I've assigned this as my reference node and labeled 3 unknown voltages, VA, VB, and VC. However, when I do KCL at node A, I need to explicitly account for the current through the voltage source. So I assign that as another variable. I have to give the unknown current a variable name, I sub s, and indicate the assumed positive direction. Unlike the currents through the resistors, I have to retain this assumed direction when doing KCL at any other nodes that might need this variable. This adds 2 additional variables to this problem. VA is treated as an independent variable, and the current through the voltage source is the second variable. In general, eliminating supernodes results in an additional 2 variables per voltage source in the circuit. Now I'll write KCL at these 3 independent nodes. At A, summing currents leaving the node, IS is assumed to be leaving, so I have a positive IS plus this current plus this current. This current is VA minus VB over 1 ohm plus this current is VA minus VC over 2 ohms. That sums to 0. At VB, I'm going to sum currents leaving that node. That gives me VB minus VA over 1 ohm plus VB minus VR, so VB minus 0 volts over 3 ohms, minus 2 amps, which enters that node. Finally, at node C, I get VC minus VA over 2 ohms plus VC minus 0 over 4 ohms plus 2 amps is equal to 0. This gives me 3 equations in 4 unknowns: VA, VB, VC, and IS. I need another equation. The additional equation is called a constraint equation, and it enforces the known voltage difference induced by the voltage source. VA is 10 volts higher than the reference node, so the constraint equation is VA is equal to 0 volts plus 10 volts, or VA equals 10 volts. For my second example, I'll write the equations necessary to solve for the voltage V in this circuit. First, I'll write the equations using a supernode. I've arbitrarily defined this as my reference and this as my independent node VA. This node is dependent and its voltage is VA minus 3 volts. If I do KCL at A, I have 2 milliamps entering, which is a negative 2 milliamps. Plus the current through here is VA minus 0 over 3 kilo ohms. Plus the current through here is VA minus 3 volts minus 0 volts over 6 kilo ohms. That's the sum of all the currents leaving the node, so that equals 0. Now my voltage V is VA minus 0 volts, so V is just equal to VA. Now let's redo the problem without using a supernode. Now KCL at A, which is an independent node, is negative 2 milliamps plus the current through the 3 kilo ohm resistor, which is VA minus 0 over 3 kilo ohms, plus the current through the source, which is another variable, IS. KCL at B, IS is now entering node B because of my assumed direction, so I get a negative IS plus VB minus 0 over 6 kilo ohms is equal to 0. So I have 2 equations and 3 unknowns. My constraint is VA is 3 volts higher than VB, so VA is equal to VB plus 3 volts. That's equivalent to saying VB is equal to VA minus 3 volts. Finally, my voltage V is VA minus 0. And I have 4 equations and 4 unknowns that I can solve for the voltage V. Finally, I want to talk about some common mistakes in nodal analysis that can result from a poor understanding of supernodes. Some people have kind of an aversion to using supernodes. They feel uncomfortable defining them, or they worry about missing one or more current terms associated with a supernode. This leads people to try to avoid supernodes completely. However, a common mistake is to leave out the currents through the voltage sources. So if you don't use supernodes, do make sure you account for all the currents, especially the currents through the voltage sources. You also need to be ready for more work solving the equations. It's worthwhile becoming comfortable with supernodes. However, if you absolutely want to avoid them, make sure you properly define all of the necessary variables, especially currents through voltage sources. Whatever you do, don't assume those currents are 0.